Hi, I'm Dylan, and today, me, Scott, Charlie, and Gary will share how strain gauges can be applied to measuring the stress in a satellite support structure inside a rocket during launch. Rockets often experience accelerations of up to 18,000 miles per hour and are subject to harsh acoustic and vibrational environment during takeoff. Measuring the stress in a satellite support structure during launch allows for the capture of dynamic characteristics of structures, including natural frequencies, mode shapes, and dampening. The real-time monitoring capability enables an immediate response in the event of an emergency. Monitoring of the structure is critical because its failure could lead to unsuccessful satellite deployment and failed mission outcomes, as well as the loss of an almost $20 million satellite. For future missions, the strain information validates designs and models of how structures are expected to perform.
So there are several challenges we must take into consideration when we're thinking about using a strain gauge on the satellite support structure. One of them is weight. Rocket launches are really expensive, costing about $10,000 per pound to send to space. The satellite support structure must be lightweight so that it can reduce the cost of the operation. Another challenge that we got to take into consideration is the thermal aspect of it. Rocket launches produce an extremely high level thermal energy. The satellite support structure must be protected so that it can withstand the heat. Radiation. Earth space radiation can cause serious problems for both the computer systems on a rocket and the structural materials. Excessive amounts of radiation will cause something called radiation hardening. The radiation will increase the strength of the material, but it will also increase the brittleness. Due to the force of the launch, the rocket will experience heavy vibration and shaking and may undergo vibration fatigue. The structure must be able to withstand the stress caused by these vibrations. Assuming that the spacecraft carrying the satellite is unmanned, there are no immediate human safety risks for this application.
So how are the strain gauges exactly used in these rocket applications? Well, the most commonly used strain gauge is the metal foil strain gauge because of its relative accuracy and good cost or low cost. As far as location, strain gauges are typically located in the member or spot that is expected to experience the most stress because that will likely be the area that fails first. For this application, we recommend a full Wheatstone bridge, so 4 active strain gauges, because in order to provide maximum sensitivity, especially if the rocket is experiencing extreme loads and high vibrations. The gauge will experience a change in resistance measured through the Wheatstone bridge's differential voltage, and then this voltage can be converted to load measurements such as the weight, pressure, tension, etc. Strain gauges are also susceptible to electronic magnetic interference, so to account for this, sensors should be spaced out at distant intervals. Taking into consideration the data output, some electronic systems will need to be on board the rocket, such as a transmitter to convert and relay the stress data back down to the Mission Control Center on Earth.
To calibrate our strain gauge, we will apply a set of loads upon the structure, measure the voltage across the Wheatstone bridge. We can graph the measured voltage by the applied load to create an equation to find the strain for the voltage. The strain will then be calculated by using the following equation. Strain equals VQ over IT, where V is the force, Q is the first moment of area, I is the moment of inertia, and T is the width of the cross section. Since we are interested in mechanical stresses, Hooke's law will need to be incorporated to convert the strain measurements into stress, and that's the following equation. Since all resistors will be exposed to the same temperature, there will not be a temperature drop across the resistors, and any change in temperature of the environment will not affect the measurement of the strain gauge. Alternative ways to measure the strain could be using a laser vibrometer. This measures the dynamic surface response of the material. It measures frequency shift of the laser beam reflected from the surface. This is a non-contact alternative solution to strain gauges, and the data collected from the vibrometer can be applied to evaluate bending strain in the structure. Additionally, you could also use a ring gauge. It works in a similar fashion to strain gauges. However, ring gauges are typically used for measuring strains in bars, axles, and on cylinders. This is our references. Thank you so much.